Hi, this is Dr. Anna, uh, your historical geology professor, and today's topic is early Paleozoic. We're going to talk about the geology of the early Paleozoic, concentrating on North America, of course. And at the end, we're going to talk about the life of the early Paleozoic. So let's start. What is amazing about this time that now we are inside the Phanerozoic. Remember that starts with the Cambrian 540 million years ago, and this is the time when we can actually really use the tools we have learned so far, because not all the rocks are metamorphosed. We have sedimentary layered rocks where you can put together the events. We have fossils you can correlate with, so it's really kind of amazing. Um, the tools we can use actually to reconstruct paleogeography is the paramagnetism, climate sensitive rocks, environment sensitive rocks, the fossils, and we also use the paleotectonic data to be able to tell what kind of situation the plate tectonic was in. So let's go through each of these to make sure that you understand what's going on. Start with the paramagnetism. This is really interesting that if you have any sediment which settles down and it has iron-bearing minerals, those low minerals will act as a little compass. So when they settle down, actually they will orient toward the Earth magnetic north. So when these minerals settling down, they will all point toward the magnetic north. So all you have to do when you go back in time to take samples from every rock, and the sample has to be oriented. So you will be able to actually put it on the map which way at the time of that rock's formation the Earth magnetic North Pole was, which is pretty powerful because we can do plate tectonics with this and we can see what has happened with the Earth magnetic field. But let's say, what is magnetic field really? All magnetic objects will produce invisible line of a force that extend between the two poles of that object. And similarly to this, you played with this in high school or elementary school or at home, wherever. So you kind of understand what's going on. If you think of the Earth actually is very, very similar to this bar magnet, and it's possessing a magnetic field which deflects the compasses on the surface on any point on the surface toward the magnetic north. So if you have a compass, you can go anywhere on the Earth. That compass's north pole will point actually toward the Earth magnetic north. So the mineral is doing the same thing when if they are iron bearing, when they settle down, they will have to point toward the Earth magnetic north at the time. So I hope you do understand that. I mean, you have had experience with this. We also know that if you look at the geographic north, which is the rotation axis, versus the magnetic north, there is a low angle in between, a tilt, and that is what we call magnetic declination. A very interesting fact we know of, and I don't know if all of you do, that actually the magnetic pole of the Earth sometimes reverses. So whatever is the North Pole right now become the South Pole, and whatever was the South Pole will become the North Pole. And it actually happens quite often. We don't really exactly understand what's going on, but most likely the fact that, the Earth has the inner core, which is solid, iron and nickel, and then around the inner core, you got this liquid outer core, which has low moving cells in them. And so therefore, this might be the cause of the Earth magnetic field. And the reason that it's actually reversing could be related to these movements in the outer core. We don't know exactly why this movement happens. However, we do know that the magnetic poles are always moving somewhat. They might not reverse completely, but we do know that they're constantly moving. And then sometimes they do reverse. And actually, the cycle of the reverse is not really exactly the same duration. It changes all the time somewhat. You can calculate averages, but changes all the time. This map shows you the wonder of the magnetic North Pole throughout the last 170 years. And we know that it's steadily been moving to the north by an average of 10 kilometers per year. There is another interesting fact about the magnetic field, that it seems like that the strength of the field has been weakened by about 10% since the 19th century. But we still don't know if that means that there is a reversal getting ready, or it's just another thing. So it seems like that it has never affected anything about life, so most likely it wouldn't badly affect us, so we don't have to really worry about this whole thing. This slide shows you the geomagnetic reversals, and as you can see that it's never really been quite periodic, you know, like the cycles are different, and sometimes they didn't even change, like during the Cretaceous it didn't change at all. Some of the Jurassic, it didn't change at all. And in the last couple of million years, it's been changing also very randomly. So even though they say that we are overdue, I mean, you couldn't really tell because there is no two times which is exactly the same. The latest reversal occurred about 780,000 years ago, and we don't really know when the next one is going to be. This is really interesting. One of the first reason that they realized that the magnetic north and south is switching is when they checked the magnetic field around the Midoceanic ridge, and this is how they knew that actually the Earth is getting wider at the Midoceanic ridges. Because if you look at the stripes of igneous rocks along the Midoceanic ridges, they always have mirror of the magnetic pole reversal. So you can see this is normal, this is opposite, normal, opposite, normal, opposite, and so on. And it's exactly the same on the other side. So that proves that actually the magma is coming up in the Midoceanic ridges and pushes the continents apart. And if you look at this movie right here, it will tell you how can we use the rock's magnetic signal to actually put the continents back. This is how we can prove that actually Pangea was together, because if you look at the magnetic north directions during the Permian, the Pangean time, they actually will point the way that you can put together the magnetic north based on how if you push the continents back together, they all the iron-bearing minerals of that time will point to the same direction, which proves that they actually were together at the time. But this movie explains it pretty good, so just check it out. Okay, the next tool is the climate-sensitive rocks, and you probably remember at the beginning of the semester we talked about that we have certain types of rocks which only form in certain environments. For example, like if you have hematite cemented sandstone, that just means usually that there was a dry climate, and the reason for it is because it was an ice age. It could also happen that if you are in a extreme continental climate in the middle of a huge continent, you also get red sandstones. If you have dune sandstone, that usually means that it's dry climate. Or if you have coal, you kind of know that it's a swampy, humid climate. So these are the climate-sensitive rocks. And then you have the so-called environment-sensitive rocks, which are actually kind of similar. Because anytime you hear about reef carbonates, you know right away that they are photic zone, that they are in the tropics. If you hear about tillites, then you know that that just means the ice rafted sediment. If you see desert sandstone, you know that it's a desert climate. Or if you have a climate-sensitive plant bearing rock layer, then you kind of know that they had to be on the continent because they would not be on the ocean. So you can actually almost put them together based on where those plants are located as fossils. And this takes us to the fossil, of course, because they can also be very important in reconstructing the ancient location of the continents. Because, you know, if you have animals that couldn't go into the water, then if they are distributed in all these continents, then the continents had to be together, otherwise the animals couldn't distribute. So it's that simple. The paleotectonic data, they're also important because if you look at the ancient faults and folds, then it can help you to reconstruct the paleogeographic maps. So these are our tools we can use, and now let's jump into the early Paleozoic. And when we're talking about early Paleozoic, we're talking about the Cambrian, the beginning of the Cambrian, all the way to the end of the Silurian. So here we are. And then the late Paleozoic starts from the Devonian, Carboniferous, and Permian, but that's the next chapter. This here is the Paleozoic paleogeography, Paleozoic paleogeography, crazy name. We know that at the beginning of the Paleozoic, there were 6 major continents. One is Baltica, and Baltica is right here. And that is basically west of Ural Mountains, which is Europe. Then we have China, and we have, China is including all Indochina and the Malay Peninsula. We have Gondwana, which is this big continent right here. And China is right here, actually. This part of the whole thing is China. Gondwana actually contains Africa, Antarctica, Australia, Florida, India, and Madagascar. Now, I don't know this, so you don't possibly, if you don't know it, it's not such a big deal. Then we have Kazakhstania, which is the extension of Siberia, and then Laurentia, which is us. That definitely, I think the 2 most important right here is Laurentia and Baltica, because at the beginning we have Iapetus Ocean in between, and Iapetus Ocean becomes a big ocean, and then it comes back together. So that's about the formation of the Appalachian, so it's kind of important. And then we also have Siberia, which is right here, and that is east of the Ural, so it's like the big Russia and Mongolia basically. This is how the late Ordovician geography looks like. It's kind of interesting that even in the Cambrian and the Ordovician, Laurentia is like laying on the equator, so the whole area is tropical. So there is a whole lot of limestone and carbonate formation during this time. And the interesting thing during the Ordovician, actually, that as you see, Gondwana moved down south. Whenever there is a pole there is a continent at the pole, everything is set up for an ice age. So most likely we had a relatively not too big, but definitely an ice age during the Ordovician, which caused some fossils to die out. And then this is the Silurian geography. As you can see, Gondwana is at the South Pole, and Laurentia is near the equator. So it's kind of interesting. And now we have to talk about sequence stratigraphy. And the sequence stratigraphy related to a guy who figured it out, and his name is Lawrence Sluss, and he was living between 1913 and 1996. He correlated 6 Protonic Sequence on the North American continent. That just means a Protonic Sequence is a really large-scale lithostratigraphic unit. Basically, he could correlate it from East America all the way to the West America. So these stratigraphic units are a transgressive, regressive. So transgressive, sea level is going up. Regressive cycle, like a transgressive, regressive cycle. and it's bounded by major unconformities. And usually, if you think about transgression, sea level is going up, so every sediment which is settled down is kind of preserved, and it followed by regression. And when there is a regression, that means sea level is going down, and this, the sedimentary rocks on the top start to hang out from the ocean. And as erosion starts, they go erode away. So usually, if you look at the cycle, the transgressive part is always preserved, but the regressive part might be kind of lost to erosion. The global correlation of this transgressive regressive sequences is what we call sequence stratigraphy. So sequence stratigraphy was actually first suggested by Lawrence Loss. So you have to remember Lawrence Loss sequence stratigraphy. This sequence stratigraphy is about the sea level is going up, the sea level going up and down over North America. And whenever a continent is covered by sea, we call it a Pyrrhic sea. And it was really kind of common on the Paleozoic North America. The Pyrrhic Sea is also called Epicontinental Sea, as it's just a large shallow body of water which covers the continent. And usually these were the result of changes in eustatic sea level, which means sea level was transgressive. And it could also be influenced by plate tectonics and the glaciations, of course. And this slide is the bad news, because this shows you these sequences, starting with really just a little bit of the Precambrian, because the first large unconformity was during the Precambrian, and the yellow always shows you the continent. So whenever you have yellow mostly everywhere, that just means it's a regression. And as the transgression starts, you know, the continent gets smaller and smaller. There will be a time when it's all ocean, and then the continent starts to grow again. That's the regressive part. So this is the transgression, and then this is the regression. So regression, transgression. So I should say T, R, and this is the R, regression. I hope you understand. So regression is when the continent starts to become bigger, and transgression when the sea starts to get bigger. So this just shows you the six sequence, starting with Sauk, Tippecanoe, Kaskaskia, Absaroka, Zuni, and Tayas. But in the Paleozoic, we just have 4 of them: Sauk, Tippecanoe, Kaskaskia, and Absaroka. So for this chapter, this 2 next chapter, which is the Paleozoic, you just have to know these 4. Okay, so and we're gonna talk about, and I do want you to know the names and their duration. Okay, and we're gonna go through this, and you will know. So the Sauk starts in the Precambrian, and it goes into the Ordovician. So Sauk sequence, Precambrian to Ordovician. Tippecanoe is Ordovician to Devonian. Kaskaskia is from Devonian to Mississippian. And Absaroka is from Pennsylvania to actually it goes into the Jurassic right there. So these are the things you have got to know, because I will ask that. So let's start with the Sauk sequence. The Sauk sequence goes from the late Proterozoic to the Ordovician, as we just said. Every single Protonic sequence actually has exactly the same, because North America has been on the equator, so it's in the tropics. So each sequence have exactly the same type of rocks in it, starting with the unconformity. On top of the unconformity, the first sediment is always quartz sandstone as the transgression starts, and then it followed by limestone, and then it followed by shale, which is the peak transgression. And then as the regression starts, the carbonate coming back, and then it finished by carbonates, which is the regression, and then boom, unconformity. That means the sea level dropped below the platform. So the rocks is now out, and they are starting to erode right away. That's the unconformity right there. So the Salk sequence starts with the unconformity, and it is during the latest Proterozoic. And at that time, the Laurentia was completely emerged. The only place there was some water is along the border where the Appalachian is. And these borders were passive margin, just like they are today, exactly the same way. And during the Middle and Late Cambrian, this transgression started, the South transgression started, and the Empiric Sea covered just about the whole of North America, except a couple of areas right here. And that is what we call the transcontinental arch. And this went all the way from Lake Superior to New Mexico, and it was some part of the Canadian Shield was actually emerged. Because North America was on the equator, like this is the paleo equator right here. Therefore, the whole area was in the tropics, and you know what kind of rocks is forming in the tropic, what kind? Yes, you're right, limestone. So this is what happened. It was a lot of limestone formation during this time, and many of these limestones containing interesting bioclasts, organic fragments of fossils, and a lot of stromatolites. Remember, the stromatolite is the blue-green algae, which is not the right name. They really are cyanobacteria, and they photosynthesize and release oxygen. These rocks also very frequently has oolitic texture. Along 81, Highway 81, I should say, we do have a lot of this limestone actually. So we walk on it, we see it all the time. When the South Sea started to regress, it happened during the early Ordovician. Most of North America became emerged, and the rocks were exposed and extreme. It was more humid climate during this time, and there was extreme karst formation. It was tropical climates, most likely humid, so that's why we had so many, I should say, caves, just collapse breccia from the caves, and a lot of karst formation, as I said. So that was the boundary between the South and the Tippecanoe sequence. One of the best examples of the South sequence is the Grand Canyon, and this shows you that stratigraphy right here, and of course with the names, but I wouldn't know them, so you don't have to know it. Just remember that the best example for the South sequence, one of the best example, is the Grand Canyon. And on this slide you have, I put down, you know, which one is the South sequence right here. So right from here to here is the South sequence, and this shows you the great unconformity between the igneous and metamorphic Precambrian rocks and the South sequence right there. So that's about the South sequence, and now we move on to the Tippecanoe sequence. The Tippecanoe also starts with an unconformity, just like all the other will be. And after the unconformity, we have a clean quartz sandstone, which we believe was a recycled quartz sandstone from the Precambrian, because this quartz sandstone is extremely clean. And the name of this formation is the Sandpeter sandstone. And then after that, because North America is still around the equator, we have carbonates, lots of reef carbonates, especially in the Michigan Basin. And these carbonates are characterized with barrier and pinnacle reef formations. And the peak transgression is represented by the shale. And after the shale, the regression starts, and we have lots of evaporates in the Tectonic sequence. So we know that the climate was very, very arid. I'm gonna finish the first six segment right here, and I will see you in the second.